Um, hello, everybody. We've got this session open, but we're going to wait just a couple minutes while people file in, attendees file in. So if you can just hold for a couple minutes, we'll see if we can't get this started at about 10:45. So thanks for your patience, and we'll get back to you in a couple minutes. Thank you. For anybody that's just joined, we're just kind of in a holding pattern for another minute or so. We see participants filing in, so give us another minute and we'll get started shortly. Thanks for your patience. Okay, everybody. So we'll get started. I just want to say welcome and hello to everybody. Thanks for joining today, and thank you for your interest in JMAG. My name is Brian Kowalczyk from PowerSys, and I just want to welcome to this session regarding advancements in material characterization in motor analysis. So one such company advancing research and development of materials is Arnold Magnetics. Today we have the privilege of Dave Farnia as our keynote speaker. David is currently the Director of Research and Development for Arnold Magnetic Technologies. And in this role, David draws on his nearly 20 years in the field of electric motors to help build a technology center in Madison, Wisconsin. The Technology Center was established in 2019 with a dual purpose of researching materials and rapid prototyping of electromagnetic devices. Working with customers to move their theoretical designs to physical hardware requires balancing performance targets against manufacturing methods. The push for manufacturable designs has given David insight into how best to model and evaluate new designs and reduce the time to move from concept to hardware. So I would like to now welcome Dave to share his presentation. Dave, the floor is yours.
Thank you. So hopefully you can hear me. So this is I guess a first for me in terms of a virtual keynote. So I'm hopeful that everything will go well, and thank you for bearing with me if there's any issues. But again, I'm very happy to be here, even if it is virtually. So hopefully the next time we have a users conference, it will be in person and have some good discussions with the various JMAG users that are in attendance here. But anyway, my name is Dave Farnia. So I'm the Director of Research and Development for Arnold Magnetic Technologies, and I was asked to give a keynote, and one of the topics that I thought would be very useful for the audience in a finite element focused conference is looking at how those designs really translate into prototypes or into production. So let's see. By way of a little background on Arnold Magnetics, we have a fully integrated supply chain. And I'm going to see if I can hide that. There, now I can see my full screen. So we have a fully integrated supply chain. So we start with the mining and processing of rare earth materials and then go into magnet production. So pressing those permanent magnet blocks, getting into magnet fabrication, or actually cutting those blocks or cutting shapes from those blocks. Permanent magnet assemblies, so making those into rotors or other electromagnetic devices, and then assembling those into larger components such as rotors plus stators, and then getting into that full system integration. So the the various aspects of this process, we support them all through our tech center, and then by prototyping and testing some of the assemblies that we're making. So where does that happen? Well, we have 11 locations now. So the Madison, Wisconsin Technology Center, that's where I'm located. We were the 10th and the newest until the acquisition of Ramco earlier this year. So Ramco is located in Greenville, Ohio. They are a stator manufacturer. So really trying to augment our capability in delivering a full completed turnkey assembly solution. But some of the other facilities that we have our FlexMag facility in Marietta, Ohio, precision thin metals, rolling the thin electrical steels in Marengo. Alnico, also in Marengo, a electromagnetics plant in Ogallala. Another FlexMag, which is a highly loaded magnetic composites in Ohio. And then the magnet fabrication in Sheffield, UK. Ludwig, Switzerland is where we get our Mercoma magnet. So we have a magnet manufacturing facility there. And then we have locations in China for both magnet manufacturing and fabrication, as well as our headquarters then in Rochester, New York. So all those plants, what do they do? Well, far left, we're the tech center. We kind of try to capture everything. So we have our hand in a lot of different cookie jars when it comes to working with the different groups inside of Arnold Magnetics. So our PMAG, Permanent Magnet Assemblies group, they're making rotors, they're making electromagnetic assemblies. PTM is rolling thin metals. Ramco is manufacturing stators, but then also induction machine rotors. EMAG out of Virginia, and then FlexMag with our rolled composite. So again, we're trying to really pull a lot of different technologies together to deliver those electromagnetic devices. It's kind of a unique perspective. So I've enjoyed working with Arnold the past several years and working on the tech center. So, but my career really goes back about 20 years. So I started simulating electric machines using JMAG roughly 20 years ago. And at that time, I was working on an electromagnetic compressor model, working in Simulink. At that point, I thought Simulink was incredibly helpful. That was still a relatively new technology at that point, and allowed me to really move that design forward and get to the point where I could simulate and then predict the performance of that compressor. And then kind of towards the tail end of that work, discovered JMAG. So JMAG model circa 2004. So right at the tail end of my thesis, went through, did a very simple 2D static electromagnetic model to predict the holding force for that linear electromagnetic device. It was fantastic. Started using JMAG at that point and really never stopped in the past 20 years. And then through that 20 years, I found that the time to obtain simulation results had dramatically decreased. So when I first started modeling, it was time intensive. So making a static model, generating the results just took days, if not weeks, just to get a simple result. As the years passed, we got better and better. So the technology improved in terms of JMAG, our ability to model more quickly, integrate with SolidWorks, integrate with a way to generate those devices. That's been fantastic. But what we've seen is then with that increasing capability, now we're going to increase our model complexity. So now our JMAG model circa 2020, and this is right off the JMAG website. So something that we also have done here at the Tech Center, looking at the loss distribution. So complex loss distributions inside of these coils, big 3D model, lots of phenomena going on. So very complex model, something that we could not have thought about accomplishing in a reasonable period of time in 2002. But as I started building these motors, so now again, started 3 years ago, build the technology center. Our goal is really to help bridge the gap between design and prototypes and production. So we've had to build these models. So the question becomes, does that model represent reality? So that's our little hand wound model there, showing some of those wires, and reality can sometimes be a little bit different. So what have I learned in the past 3 years that I've used to influence my designs earlier in that design process and really get to the point where what I'm simulating is going to represent reality. So again, past 3 years at the Tech Center, we're helping customers bridge the gap between design and production. So I've drawn a little barrier here. We've got a new customer design and then an established machine manufacturer. So when I started my time with Arnold, I was maybe over here, focused on the design and analysis of electric machines. And then at that point, I'm going to toss that over that barrier to the machine manufacturer and entrust them with the entire prototype build or production build. And at this point, now I'm over here, so I get a chance to really see what our customers are coming to us with that they need to get these into production. And typically what happens is we get a design and it's got the basic drawing template. This one's from SolidWorks. And a lot of times that initial design is just really lacking a lot of the details. So some of the notes we would expect, tolerances, just the way that we would manufacture. It's a design, and typically a design that is used for advertising. So you're going to get a motor model. Well, we're going to render it. We're going to make it look really nice. And then we're going to try to put it on the website and talk about how great it is. And so this model is no relation to anything that we have worked on here, just what I thought to be a very nice rendering of a motor from the LG website. But again, fairly representative of what we see in the sense that a lot of these initial designs, they're marketing. They're trying to gain traction and to find a niche in the marketplace. So they're going to go for extremely high efficiency, very high slot fill, very tight air gaps, high speed, laminated magnets, cobalt iron stators, or Hyperco back, really high end materials in order to get the most performance that they can from these machines. Well, they're going to take all that and they're going to try to cross that barrier and eventually they're going to get rejected. So the machine manufacturer, and then I can attest to this personally. Every time that I would ask one of the manufacturers about, okay, can we build this? Oh my, and they would shake their heads and it's more complicated than that. And I really realized that being on the manufacturing side versus on the design side, it's languages that have similar vocabularies but different intents. And so now in working with the Tech Center, that's really what we've tried to do. Add tolerances to that design, fits, look at the cost constraints, the lead times, do some further development, do some testing. So this is a carbon fiber sleeve that we're going to test wind onto a mandrel to make sure that we can achieve the appropriate tension for magnet retention on the design. And once we do all that development, now we have something that's manufacturable. So the design is great, but let's look at the constraints. So let's really look at if we have to build this, what is it going to look like in prototype or in production? So these are the common issues that we typically wind up seeing when we're evaluating an initial design. So overconfidence in some of the material properties, not really considering the manufacturing methods, or not considering how those parts are assembled. So what does that mean? Well, let's take a look at the materials. Arnold Magnetic Technologies, we're a material manufacturer. We make electrical steels, we make permanent magnets. We do a lot of testing of these different materials. We also make final end systems, so it means that we have to use a lot of materials from other manufacturers. So overall, we're somewhat agnostic to the type of material that's being used. Of course, we'd prefer Arnold's catalog of materials, but at the same time, we build permanent magnet rotors and we build stators. So we have to use the material that is going to be best suited to the customer's application. So a lot of times we're building high performance machines. This is really going to drive people to cobalt iron. So again, the backstack, the Hyperco, very high performance, high saturation materials. The challenge is though that they really need some special processing to achieve those properties. So you have to do the heat treat. You have to be very careful with how much stress you're inducing in cobalt iron. So there is some special processing that goes along with it. At the same time, cobalt iron can have a very long lead time. So these are things that should be factored into the design. Where is the design rapid? Do you have to get a prototype up and running for a demonstrator? If so, it could take longer than expected to get some of these materials in. If we're looking at the range of BH curves over here, again, yeah, vacuum flux is excellent. The base level M19 should be shown in black here. It's very common. It's available. It's inexpensive. It's easy to get a hold of. And so if you need a proof of concept demonstrator, M19 is a very nice path to go. If you're looking for that high performance, you can go to cobalt iron, but again, it's going to take some time and special processing considerations. So when we're talking about electrical steels, again, we make our own version of silicon steels here. They're rolled very thin, but we also have to characterize these materials. So we get typical properties, and these are usually the properties that are going to be published. So typical BH curves, that's going to be in the JMAG database. It's what we would utilize for performance predictions, relatively representative. So most of the time, when we take these measurements of the materials, there's not a lot of differentiation. But what happens is if we're processing some of these materials, we can affect some material changes. So if we take a look at a nominal curve over here for our material properties, and then we take a plus or minus 5%. So let's take maybe a minimum and a maximum curve for that silicon steel. At 1 Tesla, a very low saturation, and probably closer to no saturation, the difference between the low curve and the high permeability line at 1 Tesla, so at a fixed output field or fixed flux density, the field to excite that output field, the difference is about 20 amps per meter. So not really that big of a difference, even if our properties aren't as good as the nominal values. If we take it into 2 Tesla, and again, this is excessive saturation at this point for a silicon steel, that distance can go to 16,000 amps per meter. So if you're really trying to operate in heavy saturation, predictions should be taken with a grain of salt, because that performance can be dramatically affected by the way that the material is processed, and then that resulting performance can be much different than what you would predict. How does this really translate? So saturation's impact on modeling. A lot of times, again, working with JMAG, we have some simplified equations. So if we're looking at doing the DQ equivalent circuit, it works well. It's a nice way to simplify motor performance and then predict that performance. And what we'll start with is that generic torque equation. We simplify that, but that assumes this ideal performance. In reality, we do have saturation effects. And what that means is that we're going to have some fall off. We're going to have a lambda PM or a permanent magnet flux linkage that as that system is getting saturated, it's going to start to fall off. And so again, these are just things that we need to understand when we model performance, where we are at. So if we're in heavy saturation, we might have to do something differently. And again, even maybe going back to some of the efficiency maps that we saw yesterday, for the bulk of that efficiency map, a simplified model is probably pretty good. But if you're really pushing that performance out to those corner points, then you might need a more accurate representation of the material properties. Same thing on magnets. So we looked at electrical steels, permanent magnets that kind of fall into the same category. We like to use a variety of magnets when we're making rotors. Some of the samarium cobalt magnets that we would get from our Chinese facility, they have very nice properties. But we have to look at those tolerances. If we compare the basic properties for a samarium cobalt that we would get from our Shenzhen facility to a samarium cobalt that we would get from our Swiss facility, we can see that, well, the MGOE, the strength is about the same. So 29.9 to 31.5, 29.9 to 32 MGOE or mega Gauss Orsteds. All right, well, very similar performance. We start digging into that performance, we see that, well, our BR, our minimum BR for 33 is 1.14. versus 1.12. So much tighter range on our remnant flux density. Same holds for our coercivity, our HCB, the 820 to 860 versus 845 to 865. So we try to hold a much tighter range on our coercivity. Also really falls into the intrinsic coercivity, which before I got to work with a magnet manufacturer, I did not care about. So when I'm looking at the magnet model in JMAG, I care about the BR and I care about the HC. So I'm looking primarily at the second quadrant of the magnet. The magnet manufacturers will always talk about the intrinsic coercivity. So that really is determines how far you can push the magnet out at temperature. So a higher intrinsic coercivity is going to result in better temperatures resistance. So less loss or less permanent magnet property loss with temperature due to that higher intrinsic coercivity. And again, so this is where we really get into that difference. So it's critical to understand what happens to performance at the low end of the tolerance band. This goes for the neomagnets as well. So if we look at some of the Arnold grain boundary dysprosium diffused neomagnets, they're high energy products. So high energy products and high operating temperatures. It's a very novel magnet technology now that we're seeing crop up in a lot more applications because it is very high energy product, but also can withstand higher temperatures. So grain boundary diffused neos, there's patents on it. So we have to get these from our Chinese magnet vendors. So that process is again, all controlled and patented. So Arnold relies on our vendors for the material data. And if we take a look at a range, so grain boundary diffused 54 UH, 52 UH, and 50 UH. All right, well, the 54 should be better. Should be stronger than the 50 UH. But if we plot those min to max values, so the solid line showing our remnant flux density at the minimum and at the maximum value from the data sheet, and the coercivity, the HC, minimum to maximum value, what we find is that GB50UH, if we're at the high end of our range for GB50UH magnet, we're just above the low end of a GB54UH magnet. So it's really critical to understand what that range is, not just the nominal properties, but also what's the min and the max. If you get a batch of magnets, they could be at the low end of their tolerance. They're still to spec, but they could affect that performance in that end application. So again, manufacturing methods. We talked a little about some of the materials. Well, now we're going to utilize these materials and make parts. Magnets. So we reduce magnet losses with segmentation. So we're going to take our samarium cobalt magnet and we're going to laminate them. So that lamination process, the same with electrical steel, is going to reduce the losses. So our eddy current losses inside the magnets is going to be dramatically cut by segmenting our magnets. Drawback is that these magnets have to be cut from a starting block. So if we have that 1 millimeter magnet segment, we have to use a basically 1.45 millimeter block in order to get that. 1 millimeter for the actual slice and then 0.45 millimeters for the cutting blade, which means that for a 100 millimeter stack with 101 millimeter segments, we need a 145 millimeter starting block. A 100 millimeter stack with 2 millimeter segments would only need a 123 millimeter block. So the cost for that finished magnet, the finished laminated magnet, is a function both of the time to make the slices and the total amount of raw block that's required to generate that finished magnet segment. And we can think about this too. Besides having more block requirements for those thinner segments, we've doubled the number of cuts. So to go from 2 millimeters to 1 millimeter, it's twice as many cuts. So the time to process that magnet block is also going to be nearly double. And again, this just a internal documentation, or just something to kind of keep in mind when you're determining the number of segments. So use the minimum number of segments that will keep the losses in check. So once we make those magnets, then we have to bond them into the rotor. So this little rotor cross section here, the black lines show our adhesive. On very large rotors, those bond lines, they're not that big compared to the magnet. On something that's an extremely small rotor like this, the bond lines will start to affect performance. So we really need to account for the magnet volume as a function of, well, tolerances and then bond lines. At the same time, magnetization direction, very tiny Halbach array magnets. Each of these magnets is going to have a little bit of an angular tolerance. So it's not quite perpendicular. It could be anywhere from 2 degrees of, or well, up to a couple degrees off in that direction. And so is that going to have a significant impact on the end result is something that we would try to look at in the design phase. Also note these magnets are made with an EDM. So we're going to cut these or use basically a wire cutter in order to cut these magnets. That EDM method, very, very tight tolerances. If you are moving into production, most likely you're probably not going to be EDMing those magnets, especially for high volume production. So the production method for magnets might have different tolerances. Again, this is just something to consider in that design phase where what are we designing for? Is this a low volume design that's never going to go above 10, 20 units a year? If that's the case, we're probably going to be EDMing. We can probably rely on very tight tolerances. If you're in a situation where there might be thousands of units a year, it's probably not going to be EDM magnets. So we have to incorporate the production tolerances with our design. So let's take it a step further. We've seen that Halbach, multiple segments. We're all going to bond them together. Can we make it a little bit easier? And what we can do is the Halbach array magnets. What we're doing is the press or the magnetization direction. That's a function of the orientation that we press these blocks in. So that is something that is set in the block itself. If we take these individual blocks and then bond them together to form a single block, we sometimes can magnetize this as a single pole piece. So now we can bond unmagnetized blocks together, magnetize them as a single pole piece, and then make our assembly process much easier. At the same time, if we look at the tolerances, well, each of these magnets separately is going to have its own tolerance. Together, we would cut the magnet out, and then our tolerance would be covering those 3 magnets. So our stack up, if we're making a rotor with multiple segments, cutting the segments down by 1/3 is going to reduce that stack up tolerance. If we compare that performance, so let's say we have our starting point of that 0-90 degree Halbach, our 4-segment Halbach, maybe a Halbach-like. So using those 45-degree angles versus, in this case, what we call a 3-segment Halbach, performance is very similar. So we can get very similar results by using something that is a pre-bonded magnet pole to our original Halbach comparison. And in case of the 3-segment Halbach, we can actually exceed that performance. So assembling a motor, now putting everything together. Let's start on the stator. Sometimes the rule of thumb estimates just don't work. The wire layout that we have shown on the right, it's tight, but it should work. So we went through, and then once we started to build that stator, it didn't work. So we wound up having to drop some strands in hand, and the wire just could not get inserted into the slot with the process that we were using. So it's really good to check that wire fill. So even if we have a rule of thumb where we're looking at the fill factor of the slot, including the insulation system, and everything lays out correctly, we really have to build and check. And so after that, we went through and started doing 3D prints. So we are going to 3D print a stack, do a sample or a test insert on the wire, make sure everything goes in correctly, and then hopefully eliminate the potential of getting to the finished stack and not being able to get all the strands in. And I should also mention too, even with these 3D printed stators, there's flex. So a steel versus a plastic, or plastic is a lot more forgiving. So we typically try to take that into consideration as well when we're doing these sample winds. Back on the rotor, we talked a little bit about the Halbach. They're very nice rotors. Or if we are doing a permanent magnet rotor assembly, we see the advantages of going to a Halbach array. The image below shows a 4-segment, so let's say a simple Halbach array versus a 12-segment Halbach array, and we find that, yep, the field in that above the 12-segment is more sinusoidal. It's shown in black, has a higher amplitude, so the 12-segment is going to get better performance in terms of that field in an ideal case. Kind of the same with a round rotor. So if we take that that same Halbach 4-segment Halbach pattern, model it in JMAG, I'm going to put a section line right above that rotor surface, and I'm going to look at the field and then compare the field to say, okay, well, if it was a standard parallel magnet poles, so non-Halbach configuration, we'd be in the dashed black. If we do a little bit of field shaping, so let's say that Halbach-like configuration, well, we're going to get to orange. Well, if we get to a 4-segment Halbach, dashed green, and an ideal Halbach in blue. So ideally, we'd love to get 4-segment Halbachs because they're challenging to manufacture, but not overly taxing. The ideal Halbach, yeah, it's going to give you a little bit better performance in terms of that sinusoidal nature of the field. And so in some cases, we are asked to do rotors that have multiple segment per pole in a Halbach configuration. So how would we assemble that? Well, inserting magnets in the Halbach rotor, it seems easy. It is, of course, a challenge when we get to actually trying to build these rotors. When we build a Halbach rotor from a 4-segment to a multiple segment per pole, we have to build a magnetic bond fixture to hold the magnets in place while the adhesive sets up. So you got this bonding fixture. You can see all our adhesive lines. We got bolt holes that we can bolt down the magnets, hold everything in place while the adhesive sets up. And typically we'll start with an every other magnet or bonding. So we'll bond every other magnet in place. And then now the challenge becomes when we try to insert the next set of magnets. So we have our bonded magnets shown here in image 2, 1 and 3. Now we're trying to drop magnet 2 in. Well, magnet 2 does not really want to be there. So all those fields from magnet 1 and 3, they are pushing magnet 2 out. So we're fighting against those fields. We're trying to get everything to bond into place while those magnets are all fighting against each other. And what can then happen is, well, now that magnet is set in place, we're going to create this shear torque. So before we get the next magnet, so the magnet that will be adjacent to 1 in, we got magnet 2 in, well, it's torquing magnet 1. So it's really going to strain the adhesive that we would use to hold the magnets in place. In some cases, the force is going to weaken the bond enough that that bond fails. Sometimes it happens immediately. Sometimes it happens much later. So there are cases where we get to the final Halbach assembly and all the magnets have been put in place. You pull the fixture out and you walk away, and you'll hear a loud pop. So a magnet will fly out and then explode in the rotor. And so these are things that we typically like to avoid. And we would try to avoid that in that design phase, if at all possible. Once we got the magnets in, so let's say our magnets are all nicely bonded into our rotor and they're fixed. So we fixture them, we've got them to stay. The adhesive that we use to bond the magnets is really just there to hold the magnets in place until we can get to sleeving. So the retention for those magnets is really coming from our sleeve. In this case, let's say a carbon fiber sleeve. So this is one of the things that we utilize. Carbon fiber has a lot of advantages. So when compared to a standard steel sleeve, in the sense that it's not going to generate additional eddy current losses, it's lightweight, we can wind it directly onto the rotor. So yeah, it works out well for these applications. So let's say we've designed our rotor and we're going to use N45 SH magnets because they're up to about 150 degrees C. So our red arrow right here on the N45 SH curve, that's our permeance coefficient. A 1.0, that's phenomenal. So magnet manufacturers, we assume that you're trying to get to the maximum energy product for the magnet. So probably operating right about there. This kind of hard to see, but that shows that 120 degrees C. So it's starting just to fall off. So, okay, at 150 degrees C, you should be okay. But the rotor, if we sleeve that rotor with carbon fiber, that sleeve has to be cured. Well, we would try to cure the sleeve as high of temperature as we can, or as close to the operating temperature of the motor as we can. Well, you design the motor to 150 degrees C. We want to cure our sleeve at 150 degrees C. The problem is that when we're curing that sleeve, the rotor is not in the stator. So we're not in a complete magnetic circuit, which means that an SH grade magnet, we can get some demag. So we're curing the rotor at a lower temperature than it's operating at. But since the rotor is not with the stator, well, it's pushing that permeance coefficient much lower. So our actual permeance coefficient of the rotor is probably somewhere down here. At that point, now we are seeing some demag in those corners. So if we said, well, we want to operate at 150 degrees C and we need to sleeve it, perhaps we can go through and do some type of a magnetic keeper, wrap it with steel, increase the permeance coefficient of our magnets, or we can switch to a higher grade. So the SH grade should be good to 150. The UH grade should be good to 180 degrees C. So sometimes we have to over-design the magnets based on the manufacturing process. Overall, what happens though is that we're trying to balance high performance with manufacturability. So we're going to start with a simple design. Okay, well it works, but we really need to get more torque. So we're going to go to a simple Halbach configuration. Well, then we're going to take that and we're going to try to drive the torque higher by adding pole counts, but we're also going to try to improve some of the mechanical design by adding flats to make sure that we can transmit all that torque back through the rotor. Multi-segment Halbach, oh man, that would be challenging to manufacture. So let's figure out a high pole count, but simplified magnet geometry that is going to reduce the manufacturing challenges or the drop in performance that we would get from trying to assemble a number of poles together. We'll simplify it. So our end product is high performance, but also very manufacturable. And to conclude today, I think I enjoyed watching the presentations tomorrow, and I always like to see the direction that JMAG is going in terms of capabilities for finite element modeling. But maybe I might have a slight modification to Dr. Yamada's goal. I love simulation, it's excellent, but you really need to know what you're modeling. So after being involved in motor manufacturing, the failures really are from unexpected issues. If we estimate the iron losses and we use a conservative estimate, it's not going to get us the highest performance possible, but it's also not going to cause a motor failure. However, forgetting to check if the magnets can thermally survive a sleeve heat treatment process is going to cause that failure. So I would suggest periodically checking the model results by creating simple physical models of the design and then calibrate your model. So as your complexity is going up, operating only in the world of finite element analysis, you can convince yourself that you have a really, really good design. But I would suggest periodically stop, test that either by making a simple model or making a full prototype. Take the time to generate those results, calibrate your model, and then build your complexity from there. And so again, this is maybe the takeaway from my side where I would like to see high performance simulations and getting into multi-domain analyses. At the same time, coming back and then being able to check those results, recalibrate the model, and then increase complexity from there is going to give you the safest approach that when you get to your end destination, your final result model, you should be able to build the prototypes and build the production versions of those without running into huge roadblocks. So at that point, thank you for attending, and I guess I'll open the floor to questions.
Dave, thank you very much for the presentation. Great job, and we appreciate you sharing your company and your research with us. It was really insightful. Thanks.
No problem.
So with that, like Dave said, we can open the floor to questions. Please post those in your Q&A panel. So I don't have any questions coming in yet on Huva. So please please pose those. We can answer some of those for you. So Dave, I do have a question for you coming in. 1 second here. So what is the best approach to simulate a motor while keeping manufacturable aspects in mind from the beginning phases of developing the simulation?
So I think when you start modeling the system, I take a conservative approach on the design. So the database of materials in JMAG is excellent, and working from models using the JMAG material database is going to give you a very good approximation of the end performance. Even looking at some of the Arnold magnetic materials, though, on the magnet side, there's a lot of magnet choices. So sometimes it's good just to do a sanity check and then go out and ask, for this magnet grade, is it available? Is it a common grade? If I wanted to prototype, is this something that we could get easily, or is this a special order? So I would say typically iterate on that design. Start with a conservative approach, get it to the point where, okay, you're getting, the complexity is going up, build a test case. So when talking with the university or working with the UW-Madison students here, it doesn't have to be a full motor in order to test. You can calibrate your model on stripped down versions. So what specific performance parameter are you looking at? Build a simple model, check it, make sure that that is correct, calibrate your model, and then keep building the analyses from there. But it's also, there's a tremendous database of users and then information within JMAG, but also the larger motor design community. I would say just relying on some of the comments or the feedback from experts is never going to steer you, well, could steer you wrong, I guess, but it's always good to get out there and get other people's opinions on the design.
Mm-hmm. Thanks for the answer. So we have another question. So after cutting the magnets to the desired size, what kind of edge treatment do they perform?
Typically tumbling. So we would like to eliminate any sharp edges. And going back onto our magnet, the actual magnet, we don't want to have sharp edges on the magnets because the sharp edge can crack off. And so a typical process on a permanent magnet is to cut the shape, but then to do a tumbling operation to round those edges. So you have either a little small radius on all the edges or corners, or potentially a chamfer, depending on how you're manufacturing that magnet. So typically tumbling, that'll break all those sharp edges.
Great, thank you. So I have another question here coming in. So speaking of being conservative, how much margin would you give from the data available in material data sheet from vendors or JMAG? Maybe like 20%?
I cross-check the material. So it depends. Oh gosh. That's a very loaded question because it covers a lot of different materials. If you're looking at a magnet material, so if we go to the spec sheets that are on the Arnold website, again, for let's say a permanent magnet, where'd it go? The GB 40 something UH, or 50 and 54 UH. Go to the website, check the listed nominal, min, and max values. So typically when we're speccing a magnet, if a customer would come to us and say, I want to use GB50 or G54 UH magnets, we're going to check the magnets and inspect to make sure that they are within the tolerance range. the JMAG database of materials, that G54UH is only going to have the nominal properties. So I would suggest cross-checking the material on the manufacturer's website to look for those minimum values, and then look at modifying the JMAG value just to make sure that they align. So, okay, let's say a worst case scenario, I'm going to operate at the minimum point for the magnets. That's going to make sure that, all right, well, if the magnets are spec'd correctly, they're going to be inspected and tested in the design. They should line up and be within that tolerance range. It gets a little more difficult for electrical steels. So for the electrical steels, M19 is pretty robust. So the database, the data sheets that you would get for M19 are going to be fairly representative of what you would get in either a prototype or production environment. The thinner materials, they need a little bit further processing. So stacking them can be, sometimes if we get to extremely thin materials, we have to work with lamination vendors that are good at stacking very thin materials. When we get stators that are cobalt iron, it's working with the lamination vendors that are going to do the stress relief annealing. So they're going to be very careful about the stacks that they send, and then validate the performance of the finished lamination, not just, okay, well, the incoming material for cobalt iron has this behavior, it's in spec, we're going to stamp it and then ship it. We need that stress relief anneal. So that's, if you're working with cobalt iron, then at that point it's experience. So what is the material that you've gotten in and how does it compare to your predicted results, and then calibrate your model based on that data. So most of the time, take a look at the manufacturer's data sheet online, see how it compares to the nominal values that are in JMAG. High-end materials, at that point, it's just more experience than anything. So how does it actually compare or perform in that end application? Calibrate your model and then build from there.
Dave, thanks for that. And tell you what, let's slip what we're out of time, but let's slip one more in. Maybe you could give me a short 30 seconds, maybe. Here's
Okay.
the question. Does cobalt iron get excessively deteriorated by the manufacturing methods in comparison to silicon iron?
It can. Silicon steel is typically our testing when we laser cut lams, or when we stamp a silicon steel lamination, you'll want to do a stress relief anneal. When we laser cut a silicon steel, usually not necessary. Cobalt iron, we're always very careful about speccing the stress relief anneal, because without that stress relief anneal, our properties can really be degraded, whether it's laser cutting or whether it's stamping. Some vendors will try to get around that by EDMing a stack, which gives fairly good performance. But that's, again, it all needs to be spec'd out in the beginning. So processing for some of the common grades, not really going to change the performance all that much. High performance grades, yes, processing, it can play a huge role in the end performance of that high performance grade.
Okay. Thank you. Thanks for that. So I'll tell you what, we're out of time. We'll end the session. Wanted to let the participants that are still here know they can switch to the next session in Huva. And the topic again is concerning advancements in material characterization and motor analysis. And when you switch, if you have any technical issues, try refreshing your screen. So thanks to the participants, appreciate your attendance. And Dave, is likewise, thanks so much for your presentation today.
Thank you.
Really, really interesting. So we'll talk again, and I'll close the session now. We'll see everybody later. Thanks. Dave, we'll see you.
Thank you.
Okay, bye.